In this class, let us learn resonance. Resonance is an interesting characteristic of oscillating systems. When the driving frequency is nearly equal to the natural frequency of the system, the amplitude of oscillation increases. This phenomenon is known as resonance. In an LCR series circuit, the current amplitude is given by Im is equal to voltage amplitude Vm by impedance Z, where impedance Z is equal to root of R square plus XL minus XC the whole square, where XL is the inductive reactance and XC is the capacitive reactance. The current becomes maximum when impedance becomes minimum. The impedance becomes minimum when XL is equal to XC. Then XL minus XC is 0 and Z is equal to R. So the minimum value of Z impedance is R. At a particular frequency, when XL becomes equal to XC, L omega 0 becomes equal to 1 by C omega 0. Then omega 0 square is equal to 1 by LC. So omega 0 is 1 by square root of LC, or the frequency nu 0 is omega 0 by 2 pi, that is equal to 1 by 2 pi into root of LC. This frequency is the resonant frequency. Now let us see the characteristics of a resonant circuit. The condition for resonance is XL is equal to XC. Inductive reactance is equal to capacitive reactance. The resonant frequency is 1 by 2 pi root LC. Impedance Z is equal to R. It is the minimum value. The current amplitude is Vm by R. It is the maximum value. Tan phi is equal to XL minus XC by R, that is equal to 0. Therefore, phi is equal to 0. Phi is the phase difference between voltage and current. Therefore, voltage and current are in phase, and the circuit behaves like a purely resistive circuit. Voltage across inductor and capacitor are equal and out of phase. So the vector sum of the two voltages VL and VC is 0. So the effective voltage V is equal to voltage across the resistor, and the power dissipated in the circuit is maximum. Let us see the variation of current amplitude with the frequency. As the frequency increases, the current amplitude increases and reaches the maximum value at resonant frequency omega 0. As the frequency becomes greater than omega 0, the current amplitude decreases. The variation of impedance with omega. At the particular frequency omega 0, impedance becomes minimum, and when omega greater than omega 0, impedance increases. The important application of resonance is in tuning circuit of radio or TV. In tuning, the resonant frequency of the tuning circuit, which is an LCR circuit, is made nearly equal to the frequency of the signal of a particular station. When this happens, the amplitude of signal becomes maximum. Now let us say the sharpness of resonance. It is a measure of the quality factor. Quality factor is denoted by Q. If the resonance is less sharp, the tuning of the circuit will not be good. Less sharp the resonance, less is the selectivity of the circuit. So the quality factor or Q factor is defined as the ratio of resonant frequency to bandwidth of the circuit. Resonant frequency omega 0 by bandwidth to delta omega. The graph shows the variation of current amplitude with frequency for two different circuits, circuit 1 and circuit 2. For circuit 1, the bandwidth is less compared to the bandwidth of second circuit. So the circuit 1 is more sharp, or the quality factor is more for circuit 1. So Q factor is also equal to voltage across the inductor by voltage across the resistor at resonance, or it is the ratio of inductive reactance to resistance at resonance. At resonance, inductive reactance is equal to capacitive reactance. So we can write the equation as Q is equal to 1 by omega 0 C R. Or let us substitute for omega 0. Resonant frequency omega 0 is equal to 1 by square root of LC. Then we can write the expression for Q factor as root L by R root C. Or the quality factor is inversely proportional to resistance. As the quality factor increases, resistance decreases. So for the first circuit, resistance is low compared to the second circuit.